So, hi everyone. Welcome to today's ISDSA workshop on Causal moderated mediation analysis. And today we are very delighted to have Dr. Xu Qin as our speaker. Dr. Qin is a
Do we lose Lingbo? Can everyone hear Lingbo?
sorry, I don't know, my laptop just out of service, but yeah, can everyone hear me?
Yeah, no problem. Thank you.
Okay, I'll continue. Sorry about that. So, Dr. Chin's research focuses on solving cutting-edge methodological problems in Causal mediation analysis and multi-level modeling. She is also interested in using rigorous and innovative quantitative measures to evaluate impacts of interventions and the underlying mechanisms. And in today's workshop, the purpose is to introduce the general definition, identification, estimation, and sensitivity analysis for Causal moderated mediation effects on the potential outcomes framework. And you will also learn how to use user-friendly R package to conduct the analysis and realize analysis results. The workshop will last about 3 hours, and during the course, if you have any questions, please feel free to ask in the chat or raise your hand. And the materials can be found in email previously sent by Dr. Qin, but I can also send a copy in the chat later if anyone needs the copy. And yes, the materials, the recordings will be shared after we complete this workshop. And if you have any questions or technical problems, you can ask in chat. If you don't have any questions now, I'll now pass it to Dr. Qin.
Thank you so much, Lingbo, for the nice introduction. And thank you everyone for attending the workshop. Today, I would like to introduce some basic knowledge about causal moderated mediation analysis. And I'm going to introduce the methods first, and then we're going to introduce how to implement the methods using R. Let's take a look at today's outline first. First of all, we're going to introduce the background of mediation analysis and moderated mediation analysis. And then we're going to have some knowledge about potential outcomes framework. After that, we're going to introduce causal mediation analysis and causal moderated mediation analysis, including definition, identification, and estimation. And then we're going to introduce sensitivity analysis for causal moderated mediation analysis. In the end, we're going to learn some R package implementations. We're going to have some small exercises using R in the end, so you're expected to have already installed the R Studio and R package. And as Lingbo said, all the questions are welcome during the course. You are welcome to type in your questions in the chat window or directly raise your hand. Okay, now let's begin from the background of mediation analysis. What is mediation? Mediation uncovers the black box underlying the impact of a treatment on an outcome. It helps understand the mechanisms, pathways, and intermediates whereby a treatment affects an outcome, and thus answers the question of why and how. The mediator represents the generative mechanism through which the treatment is able to influence the outcome. Mediation analysis decomposes the total treatment effect into an indirect effect transmitted through the hypothesized mediator as represented by the blue pathways in this hypothesized diagram, and a direct effect representing the contribution of other unspecified pathways as represented by the green arrow. Why is mediation analysis of interest? First of all, it is for explanation and understanding of why and how the treatment or the intervention impacts the outcome. And it helps confirm and refute theory underlying the relationship between the treatment and the outcome. It refines an intervention by improving components of the intervention that transmit a large portion of the treatment impact or discarding components that are not important. By decomposing the total impact of the treatment on the outcome, we're able to tell how each component of the intervention works. If we find that the indirect effects transmitted through some components are very small, we may just directly discard those components and devote more effort to improving the components that transmit most portion of the total intervention impact. And it also helps us understand why an intervention is found to have a null or negative effect on an outcome. It's also helpful when we're not able to intervene on the exposure, but may eliminate a detrimental effect of an exposure by intervening instead on some particular mechanism. So in these cases, mediation analysis is of particular interest, and more details can be found in the textbook written by Vanderwell in 2015. Now, let's take a look at a specific example to have a better idea about mediation analysis. We're going to use National Evaluation of Welfare to Work Strategy Study as an illustration. And in our R implementation, we're also going to use this example. The study randomly assigned 694 participants who were mostly low-income single mothers with young children. And they were assigned to the LFA program. About 2,000 were assigned to the LFA program that aimed at moving low-income parents from welfare to work by providing employment-focused incentives and services. And the other 486 individuals were assigned to the control group, which received aid from the Aid to Families with Dependent Children program without requirement for working. And the mediator of interest in this example is if one was ever employed during the 2-year period after randomization, and the outcome of interest is maternal depression at the end of the 2nd year after randomization. And our hypothesized mediation mechanism is that attending the LFA program would increase an individual's chance of being employed, which would subsequently decrease his or her depression level. In other words, employment mediates the effect of LFA on depression. And as represented by this hypothesized mechanism, employment is the mediator, which transmits the impact of LFA on depression, so that the total effect of LFA on depression can be decomposed into an indirect effect transmitted through employment as represented by the blue arrows, which is the change in depression attributable to the LFA-induced change in employment rate. That means the LFA induced some change in the employment first, and the LFA-induced change in employment rate further changes depression. Another component of the total effect is direct effect, which is the impact of LFA on depression without changing employment rate. That means directly. So that means LFA directly affects depression, or LFA affects depression through other possible pathways. And so now we're going to introduce some traditional mediation analysis methods. One most commonly used method is path analysis model, which includes one mediator model, which regresses the mediator on the treatment. And so the pathway from the treatment to the mediator can be captured by the coefficient of the treatment in the mediator model. Here, I want to mention that different papers use different notations. You may be more familiar with the ABC notations. Here, I use superscript to denote which model the parameters are from, and use subscript to denote which predictor the coefficient is for, so that it is easier to tell what each parameter stands for. Especially in our moderated mediation analysis, when there are more parameters, if you use ABC, it's hard to tell which coefficient is for which mediator or moderator. So we use different notations from the literature. And the path analysis model also includes an outcome model, which regresses the outcome on the treatment and the mediator. And the coefficient of the treatment in the outcome model represents the path from the treatment to the outcome, and the coefficient of M in the outcome model represents the path from the mediator to the outcome. So that the indirect effect is defined as a product of the path from the treatment to the mediator and the path from the mediator to the outcome. And the direct effect is defined as the path from the treatment to the outcome. So this is a general picture of path analysis, which is very straightforward. However, there are some limitations of the traditional structural equation modeling or path analysis. First of all, they do not carefully account for confounders. Omitting confounders of the treatment mediator treatment outcome and mediator outcome relationships from the analysis would result in biased indirect and direct effect estimates. And here, by confounder of the treatment mediator relationship, I mean a variable that affects both the treatment and the mediator. If the treatment is randomized, there are no confounders of the treatment mediator treatment outcome relationships. However, even if the treatment is randomized, the mediator values are typically generated through a natural process rather than being experimentally manipulated. As a result, individuals displaying different mediator values tend to differ systematically in many aspects that would confound the relationship between the mediator and the outcome. That means the variable may affect both the mediator and the outcome. For example, participants who are less willing to accept a low-wage job before participating in the study might be less likely to be employed and suffer from more severe depression if assigned to LFA in particular. So in this case, willingness to accept a low-wage job before the study or at baseline affects both the mediator and the outcome. So it confounds the relationship between the mediator and the outcome. Another limitation of the traditional path analysis is that they ignore the common treatment by mediator interaction. Treatment effect may be generated not only by changing the mediator, but also by changing the relationship between the mediator and the outcome. For example, employment here in our example is the mediator. may be more beneficial to psychological well-being, which is the outcome, under the elephant condition than under the control condition. So in this case, the mediator outcome relationship differs under the two treatment conditions. This indicates a treatment by mediator interaction. So far, I have introduced the background of mediation analysis, including the traditional methods and their limitations. Any questions for now? Okay. So if you have any further questions, feel free to type in the chat window. I'll check that periodically. Now let's move on to the next section, background of moderated mediation analysis. So as we introduced just now, mediation analysis answers the question of how and why by uncovering the mechanism through which a treatment effect is generated. And moderation analysis answers the question of for whom or where by evaluating the heterogeneity in the treatment effect across different subpopulations. And a combination of mediation analysis and moderation analysis integrates the investigations of how, for whom, and where. In particular, moderated mediation assesses the heterogeneity of the mechanism, while mediated moderation assesses the mechanism of the heterogeneity. And this workshop will focus on moderated mediation. So we are particularly interested in the heterogeneity of the mediation mechanism. Now, the question is, why is moderated mediation analysis of interest? The importance of investigating the heterogeneity of the impact of an intervention has become increasingly valued. Important research questions include whether the intervention impact is generalizable across individuals and contexts, for whom and under what context the intervention is effective, and why. To answer such questions, it is necessary to unpack the underlying mediation mechanism and assess how it is moderated by individual and contextual characteristics. And a moderated mediation analysis may review a need to refine the intervention theory and may suggest ways to improve a program by tailoring the program components to different individuals under different contexts. And here I want to briefly mention the pretreatment nature of moderator. An explicit moderator defines subpopulations between which the mediation mechanisms may differ. Mueller and colleagues emphasize the pretreatment nature of the moderator and describe this as a measure of some stable individual or contextual differences that are assumed not to be affected by the treatment, yet are related to different mediation mechanisms. So by pretreatment here, we mean before the treatment. So the moderator in this course is measured before the treatment, or it is not affected by the treatment. It is unchanged over time. Although this course is focused on a pretreatment moderator, which is measured before the treatment or stable over time or unchanged over time, a moderator does not have to be pretreatment. If a moderator is concurrent with the mediator, the estimation and inference stay the same while the definitions and identification assumptions change. And a moderator may also be a sequential mediator. That means the treatment affects the moderator, which further affects the mediator. It's also possible that the treatment affects the mediator, which subsequently affects the moderator. In this case, the moderator and the mediator serve as sequential mediators, essentially. And we need to conduct the mediation analysis for sequential mediators that interact with each other. So on this slide, I want to emphasize that a moderator can be as simple as measured before the treatment and may also be as complex as measured concurrently with the mediator or sequentially with the mediator. In this course, we focus on a pre-treatment moderator. Any questions here? Okay. Now, let's take a look at this hypothesized and moderated mediation mechanism. I hope you still remember this hypothesized and mediation mechanism of our news example, in which LFA affects depression through employment. And in our moderated mediation analysis, we further incorporate moderators, including individual and contextual characteristics, such as baseline welfare amount and number of children. These moderators may moderate any pathway that transmits the impact of LFA on depression, while they are measured at baseline or before the treatment. Before introducing the causal methods, we're going to briefly talk about the traditional moderated mediation analysis method. The target parameter is the conditional indirect effect given values of moderators, which we denote as W here. And traditionally, people estimated the conditional indirect effect by extending the path analysis models. Remember, earlier we introduced that the path analysis model includes a mediator model and an outcome model, and the coefficient of the treatment in the mediator model and the coefficient of the mediator in the outcome model, their product defines the indirect effect. Well, in the moderated mediation analysis, people estimate the conditional indirect effect for each subpopulation. So they fit separate models and estimate the indirect effect within levels of the moderators. So they are able to obtain the conditional indirect effect within each subpopulation. And alternatively, researchers incorporated the moderators and their interactions with the treatment and or the mediator in the model and defined the conditional indirect effect as a function of moderators under different scenarios. So in the first case, when they fit separate models within levels of the moderators, they actually allow the moderator to interact with all of the coefficients in the median outcome models. Well, in the second approach, if researchers assume some interactions to be now, then they can save some power, but it relies on strong model-based assumptions. And the first option and the second option are equivalent if all the interactions are included in the second option. As I said, if some interactions are assumed to be now in the second option, then the first option has a lower power. And so earlier we discussed how to estimate the moderated mediation. And to assess if the mediation mechanism is significantly moderated, we may assess if the interactive factor significantly varies by moderators, and several methods have been proposed. The first is to test the significance of the interaction of the moderator with the path from the treatment to the mediator or the path from the mediator to the outcome. However, researchers have proved that this is not equivalent to the significance of moderated mediation. So this approach is problematic. That means you cannot separately test the significance of the interaction of the moderator with either path included in the indirect effect. And the second approach is the Hayes index, which uses one single index to measure the relationship between the indirect effect and the moderators. However, it applies only if the indirect effect is a linear function of moderators. And the third way is to test the difference in the indirect effect between two given sets of values of moderators. And the third way is more recommended. Despite the rich literature on moderated mediation analysis, especially in quantitative psychology or in broader social sciences, three major problems remain unsolved under this traditional framework. First of all, they pay less attention to the influence of confounders. And as I mentioned earlier, ignoring confounders of the treatment mediator, treatment outcome, or mediator outcome relationship would generate biased results, and failure to assess the influence of unmeasured confounders may result in misleading conclusions. In addition, there is no general definition of the conditional indirect effect available beyond specific mediator and outcome models. And that means the conditional indirect effect is defined differently under different scenarios. For example, the conditional indirect effects are defined in different ways if only the TM path or MY path is moderated, or if both TM and MY path are moderated, etc. So there is no general definition available. And the last limitation I want to mention is that when either the mediator or the outcome is binary, or when the mediator or outcome model is nonlinear, moderated mediation analysis has not been developed under the traditional framework to the best of my knowledge. So now we have finished the second section, which is focused on moderated mediation, in which I introduced some background knowledge and the traditional methods, including their limitations. Any questions so far? Okay, now let's move on to our next section. We're going to discuss how to overcome the limitations under the potential outcomes framework. Under the potential outcomes framework, every individual has a potential outcome corresponding to each level of the intervention, manipulation, or treatment. It is called potential because only one outcome is observed, depending on which level the individual is assigned to, while the outcomes under the other levels are unobservable. The idea of potential outcomes is frequently used in contemporary culture, for example, in movies. Some of you might have watched this movie, It's a Wonderful Life. This is a 1946 American Christmas fantasy drama film. In this movie, the leading role, George, becomes very depressed and states that the world would have been a better place if he had never been born. At the appropriate moment, an angel appears and shows him what the world would have been like had he not been born. What actually happened in the real world with George in it is observed, and the angel shows George what would have happened in the counterfactual world without him in it. And on the left, we show the observed world, and on the right, we show the counterfactual world. For example, George's younger brother, who was in actual life a World War II hero in the counterfactual world, drowned in a skating accident at age 8 because George was not there to save him. A second example is a pharmacist. George was his apprentice in his childhood. In the counterfactual world, he mistakenly put poison in pills and was imprisoned for manslaughter because George was not there to catch the error as he did in the actual world. And In reality, his beautiful wife Mary lived a happy life. In the counterfactual world, she never married and was very lonely. George had a happy life in the real world with 4 lovely kids living in a warm house. However, if George had never been born, the place where his family lives is just a ruin because George and Mary had never rebuilt it. By comparing the entire stream of events in the actual world with George in it, and the entire stream of events in the counterfactual world without George in it, the android helped George realize how big the causal effect of his life is on the other people's happiness. So the movie tells us that your life means a lot to others, so be always positive about your wonderful life. And the key message that we learn from this story for this course is that the causal effect can be defined as a comparison of the potential outcomes for the same unit. In the movie, George gets to observe both. However, in reality, we would never be able to see both worlds. But we can use this logic, use this idea to guide us to define the causal effects in a more general way. And we're going to see that more clearly when we step into the next section on causal mediation analysis. Any questions so far? So we're going to define the potential mediator and potential outcome first. For each individual I, we define the potential mediator as a function of the treatment. So MI1 indicates potential employment status, which is the mediator in our example. If 1 was assigned to the LFA group, that means T equals 1. And MI0 indicates one's potential mediator if assigned to the control group. Here, please note that we define a potential mediator for every individual. So every individual potentially has 2 potential mediators, one under the LFA condition and the other under the control condition. Although in the real world, one can only have 1 potential mediator observed. That means if 1 was actually assigned to the LFA group, then only MI1 can be observed. But if 1 was actually assigned to the control group in reality, then only MI0 can be observed, while the other is unobserved. And similarly, we could define the potential outcome. So YI1 can be used to denote the potential outcome if assigned to the LFA group. Because outcome is affected by the treatment and subsequently by the mediator, the potential outcome can be defined as a function of treatment and potential mediator. So YI1 can be equivalently written as YI1 MI1. And similarly, we can define the potential outcome under the control condition, which is YI0. And because as we mentioned, the potential outcome can be defined as a function of both the treatment and potential mediator, so it can be equivalently written as Y0M0. So far we have defined the potential mediator and potential outcome under each treatment condition. Now we're going to introduce a trickier potential outcome, which is completely counterfactual. It is written as Y1M0, which is the potential outcome if 1 was assigned to the LFA group. Well, the potential mediator takes the value under the counterfactual control condition. This can never happen because if 1 was actually assigned to the LFA group, then the potential mediator actually takes MI1. It is not MI0. But we do need this quantity to define the indirect effect. You're going to see that more clearly later. And similarly, we can define y, 0, and 1, which is the potential outcome if 1 was assigned to the control group, while the potential mediator takes the value under the counterfactual LFA condition. And these potential mediator and potential outcomes are defined under the Sutva assumption, which is stable unit treatment value assumption, including no interference. That means an individual's potential mediators do not depend on other individuals' treatment status. For example, this assumption would be violated if an individual had higher chance of being employed when both the individual and his or her best friend were assigned to LFA than when the individual was assigned to LFA, but his or her friend was assigned to the control group. That means the individual's potential mediators depend on other individuals' treatment status. In this case, the assumption would be violated. And in addition, an individual's potential outcomes do not depend on other individuals' treatment status or mediator values. For example, this assumption would be violated if an individual's depression level depends on his or her best friend's treatment assignment or chance of being employed. And you may tell that in the classroom setting or in a school setting, when the students are from the same classroom, there may be interference, in which case the assumption would be violated, so that we're not able to define the potential outcome in the way that we defined earlier. So in this case, the potential outcomes would be defined in a more complex way. The potential outcome will not be defined only as the individual's own treatment status, but also other individuals' treatment status. So that would be much more complicated. It was discussed in a Vanderwall textbook and also Guanglei Hong's textbook. The references are included at the end of the slides. But here we discussed a more common case or more widely discussed case in which there's no interference. But you may want to keep in mind that in reality, particularly in school settings, this assumption may be violated. And in addition, we also assume no hidden variations of treatments. There's only one version of each treatment level. For example, this assumption would be violated if LFA program has different versions of implementation. So you want to be cautious when defining the potential mediators and potential outcomes. You want to assess whether the assumptions are violated or not first. And suppose these assumptions hold, we're going to define the indirect and direct effects correspondingly. Any questions so far about the assumptions or the definitions of the potential mediator and potential outcome? If not, we're going to move on. And,
I had
uh-huh.
for on the last slide, if the assumption that, for example, like the LFA had different versions of implementation, could you just code it like if there were 3 mediator groups?
Yeah. Oh, in that case, you would have multiple it's not the mediator. So here we're talking about the treatment, right?
Right.
LFA,
Yes.
yeah, that is the treatment. Yeah, that means you're gonna so for example, LFA program has one version, has 2 versions, then the treatment levels are no longer 1, 0. It can be coded as 1, 2, 0. 1 means LFA version 1, 2 means LFA version 2, and 0 is the control group. In that case, you're gonna compare the effectiveness amount, the 2 versions in the control group.
Okay, but if that is like, so the assumption would be violated if there were like different effectiveness within the same version?
The assumption, so if the program has, for example, two versions, but you define the potential outcome only as y1 and y0, in that case, the assumption would be violated.
Okay, thank you. Thank you.
Yeah, but that's a good question. Thank you. Any other questions? Okay. And now we're going to define the indirect and direct effects based on the potential outcomes that we defined earlier. So let's take a look at this y1m1, which is the potential outcome under the LFA condition. And y0m0 is the potential outcome under the control condition. And y1m0, as we mentioned, is completely counterfactual, which is the potential outcome if one was assigned to the LFA condition while the potential mediator takes the value under the counterfactual control condition. So in order to define the indirect effect, let's try to recall what indirect effect is. It actually reflects how the treatment-induced change in the mediator affects the outcome. That means we want to see the change in the potential mediator first and see how much such change in the potential outcome affects the outcome while the treatment is unchanged. Now, try to think about which two cells we should compare if we want to see how the treatment-induced change in the mediator affects the outcome while treatment is unchanged. I believe most of you have already had the answer in mind. We're going to compare these two potential outcomes. Well, the treatment is held at 1, while the potential mediator is changed from M0 to M1. In the literature, this is widely known as natural indirect effect. It is also called total indirect effect. Now, let's see how to define the direct effect. Direct effect means that we want to see how treatment affects the outcome without changing the mediator. So we want to hold the potential mediator constant while only changing the treatment from 0 to 1. Now, you should also have your answer in mind now. We're going to compare the two potential outcomes at the bottom, in which we only change treatment from 0 to 1 while holding the potential mediator at M0. This is widely known as natural direct effect, which is also known as the pure direct effect. And you may notice that so far we have defined the indirect and direct effects using these three potential outcomes, but we have never discussed this potential outcome yet. If we're gonna focus on this counterfactual potential outcome, we're gonna have another set of definitions of indirect direct effects. Now, again, doing the same exercise, try to think about how to define the indirect effect using these potential outcomes. Which two potential outcomes are you going to use to define the indirect effect, which reflects how the treatment-induced change in the mediator affects the outcome without changing the treatment? Yes, we're going to compare these two potential outcomes. We control the treatment at 0, while changing the potential mediator from M0 to M1. This is known as pure indirect effect. And again, the last exercise, how to define the direct effect, which is the effect of the treatment on the outcome without changing the mediator. So the potential mediator is held constant while the treatment is changed from 0 to 1. Yes, the answer is the comparison of the first two potential outcomes in the first row, which is known as the total direct effect. So far, we have introduced two sets of definitions of indirect and direct effects. Let's summarize them. So we try to decompose the total effect into two components, and we introduce two different ways. Decomposition one is more widely used. We decompose the total treatment effect, which is a contrast of Y1 and Y0. Y1 can be alternatively written as Y1M1, and Y0 can be alternatively written as Y0M0. By introducing Y1M0, we can decompose it into a natural indirect effect and a natural direct effect. And the second decomposition introduces Y0M1 instead. So the total effect can be decomposed into a pure indirect effect and a total direct effect. And you may answer, what is the, you may question, what is the relationship between the two decompositions? In fact, the two decompositions are not equivalent in the presence of treatment by mediator interaction. That means when the treatment-induced change in the mediator affects the outcome differently under the two treatment conditions, the two decompositions are different. However, if there's no treatment by mediator interaction, that means the treatment-induced change in the mediator affects the outcome in the same way under two treatment conditions, then the two decompositions are exactly the same. Well, if you read some causal mediation analysis papers, you may notice that the first decomposition is more widely discussed, the natural indirect effect, natural direct effect. However, I would like to draw your attention that this is not the only decomposition. There is an alternative decomposition, which is not equivalent to NIE and NDE when treatment interacts with the mediator when affecting the outcome. And the difference between the two decompositions gives the definition of natural treatment by mediator interaction effect. This interaction effect is equal to the difference between the two indirect effects and is also equal to the difference between the two direct effects. Then you may have the question that which decomposition should I use in a causal mediation analysis? So here, you may notice that if we replace TIE in the decomposition with, if you look at this part, you will see that TIE is equal to PIE plus the interaction effect. So if you replace TIE with PIE plus the interaction effect, or replace this TDE with PDE plus the interaction effect, you can obtain the three-way decomposition. So the total treatment effect can be decomposed into two pure indirect direct effects plus the interaction effect. This three-way decomposition, I think it is I always recommend using three-way decomposition so that you are able to see how the indirect effect works purely and how the direct effects works purely, which have nothing to do with the interaction. And you can also look at the interaction separately. So decomposing the total treatment effect into three components allow us to separate the treatment by mediator interaction from the indirect and direct effects that have nothing to do with the interaction. Any questions so far? Here, I want to add that, as I mentioned earlier, the mediator, may purely transmit the impact of the treatment on the outcome. And it may also transmit the impact of the treatment on the outcome by interacting with the treatment. And in this three-way decomposition, we're able to separate them. We can tell how much the mediator purely transmits the impact of the treatment and the outcome, and how much the mediator transmits the impact of the treatment on the outcome by interacting with the treatment. You're able to separate them, which allows you to investigate the mediation mechanism in a more comprehensive and rigorous way. Any questions? Okay, so far we have defined the indirect and direct effects under the potential outcomes framework. Now I want to summarize the definitions in this form so that in the future, when you forget how to explain each effect, you can come back to this table and refresh your mind. You may notice that earlier we focused on a binary treatment. We only discussed t equals 1 and t equals 0, but in many of your real examples, your treatment may be continuous. So, or it may have more than 2 categories. If that is the case, we can replace 1 and 0 with any 2 different values of the treatment, t and t prime. And when the treatment is binary, t equals to 1 and t prime equals 0. So here in this form, I simply replace 1 and 0 in our previous definitions with t and t prime, respectively. And this is the natural indirect effect, natural direct effect, this is our decomposition 1. Alternatively, we can decompose the total treatment effect into pure indirect effect and total direct effect. And by comparing the 2 decompositions, we can define the natural treatment by mediator interaction effect. And here I want to add that if the outcome changes linearly with the treatment, it is fine to choose any 2 different values that are 1 unit apart. I mean, when you choose, because I noticed that when the treatment is continuous and you define the effects by contrasting 2 different treatment values, you may have a question that which 2 values should I choose? So if the outcome changes linearly with the treatment, it is fine to choose any 2 different values that are 1 unit apart. So it applies to any 2 treatment values that are 1 unit apart on the real line. However, if that is not the case, if y changes non-linearly with the treatment, you may check the effect at different sets of t and t prime. Alternatively, you may dichotomize the treatment, but as you may know, it loses information. So this is the last page about the definition. Any questions? As we mentioned earlier, under the potential outcomes, we begin from the definition, which relies on the Sutpha assumption. After that, we're gonna come to the next stage, which is called identification. What does identification mean? And you're gonna have a better idea about that after this slide. For illustration purpose, we assume that there are only 8 individuals in the population. And the definition of the causal effects relies on 4 potential outcomes of every individual, as we have learned earlier. However, as illustrated in this table, among the 8 participants who were assigned to LFA, the first 4 were assigned to LFA, for whom the only observables are MI1 and Y1M1. And the last 3 potential outcomes, as the other three potential outcomes, y0, m0, y1, m0, and y0, m1 are not observed for these individuals who were assigned to the LFA group. And the last four individuals were assigned to the control group. So for them, the only observables are which potential outcomes? Yes, y0, m0. And the other three potential outcomes are not observed. Because of the missingness, we cannot directly obtain the population average of each potential outcome, which is what we're interested in. Because our goal is to estimate the population average indirect direct effects or the conditional indirect direct effects. We take an expectation or conditional expectation of the individual specific potential outcomes. However, due to the missingness, we're not able to directly obtain them. Therefore, causal inference is essentially a missing data problem. The key lies in how to infer the counterfactual quantities from the observed data so that we can identify the population average potential outcomes and correspondingly the causal effects. So in summary, identification tries to unobservable quantities to observed data. Now you can understand that in causal inference, we begin from the definition, which involves unobservable quantities. In order to relate those to observed data, we come to the stage of identification. Let's take a look at this graph. This blue oval represents the range of y0, m0 for all the individuals. It is the potential outcome if an individual did not attend the program. And this blue oval represents the range of y1, m1 for all the individuals. It is the potential outcome if an individual attended the program. And the average of y0, m0 over all the individuals is at this level, as represented by this blue dot. And the average of y1, m1 over all of the individuals is at this level, as represented by this blue dot. By taking the difference between the two true averages, we define the average causal effect of LFA on depression. If we conduct a randomized experiment so that individuals are randomly selected to attend the program or not, therefore, the individuals who did not attend the program or the intervention, as represented by the orange dots, are representative of the population in which everyone has the potential now to attend the LFA condition. Correspondingly, the average of the observed outcomes of the individuals who did not attend the LFA intervention is exactly equal to the corresponding true average. Similarly, the average of the observed outcomes of the individuals who actually attended the, I think that this part is the control group and this part is the LFA condition. Similarly, the average of the observed outcomes of the individuals who actually attended the LFA condition is also equal to the corresponding true average. And the average causal effect can therefore be identified through the observed mean difference in the outcome between the two groups. And this is the case when the treatment is randomized, under which the ignorability assumption is satisfied. So in short words, we mean that if the treatment is randomized, then the individuals who were actually assigned to the LFA group can be representative of the whole blue oval, which represents all of the potential outcomes under the LFA condition. So the mean of the observed outcome among those who were actually assigned to the LFA group is equal to the average of everybody's potential outcome under the LFA condition. It's similar for the potential outcome under the control condition. So that when the treatment is randomized, the total treatment effect can be identified simply through a mean contrast of the observed outcome between the LFA group and the control group. However, if the treatment is not randomized, then what would happen? As you can see here, if the treatment is not randomized, this is just the one special case. The control group, the individuals who are actually assigned to the control group may be just closely gathered around here, as represented by the orange dots, while those who were actually assigned to this is the control group. Those who are actually assigned to the intervention group may be gathered here. Then the consequence is that the observed mean, simple mean of the outcome in the control group is no longer equal to the population average of the potential outcome under the control condition. And similarly, the observed mean of the outcome from the intervention group is no longer equal to the population average of Y1. And so that the total treatment effect cannot be identified through the simple mean of the observed outcome between the two groups. So this figure represents what would happen if treatment is not randomized, in which case the treatment effect can be identified under the strong ignorability of treatment. So although the treatment effect is no longer able to be identified through the observed mean outcome difference, it can be still identified if such assumptions hold. First of all, there is no unmeasured confounder of the treatment outcome relationship. In other words, the treatment is as if randomized within levels of the pre-treatment covariates. And it relies on positivity assumption too. In other words, within levels of pre-treatment covariates, every individual has a non-zero probability of receiving each treatment level. This assumption would be violated if an individual or if one or more subgroups are never or rarely observed to receive a treatment level, in which case no or little information would be available for inference about those subgroups' counterfactual outcome. Because as you know, the idea of this identification is that in the simplest case, if the treatment is randomized, then the individuals who were actually assigned to the control group actually provide the information, the counterfactual information of Y0 for those who were assigned to the LFA group. And similarly, those who were assigned to the LFA group provide the counterfactual information of Y1 for those who were actually assigned to the control group. So we do need in the individuals to provide a counterfactual information for those in the other group. But in your sample, if there are no individuals, that means if one or more subgroups are never or rarely observed to receive a treatment level, in this case, no or little information would be available for inference about those subgroups' counterfactual outcome. And the resulting sparsity in the data may increase bias with or without an increase in variance and can threaten valid inference. So the assumption is more likely to be violated at a smaller sample. When you have a large sample size, usually you would not need to worry too much about the violation of the positivity assumption, because there are always individuals who can provide the counterfactual information in each subgroup when the sample size is large enough. So far, we use these two plots to illustrate the identification of the total treatment effect. But as we mentioned, this course is focused on mediation and moderated mediation. So what about the identification assumption for causal mediation analysis? we're going to extend that to sequential ignorability. So before introducing the sequential ignorability, I would like to know whether you have any question about the ignorability of the treatment that I introduced earlier. Okay, so I know you may need some time to digest the materials, and if you have any questions coming up when you review the materials, please feel free to email me. Now we're gonna move on to sequential ignorability, which includes two parts. Why is it called sequential? Remember, the mediation mechanism is essentially a sequential process. The treatment affects the mediator first, which subsequently affects the outcome. So the first part of the ignorability is the strong ignorability of the treatment. That means there is no unmeasured confounder of the treatment mediator or treatment outcome relationship. In other words, the treatment is as if randomized within levels of pre-treatment covariance. That means after conditioning on those observed pre-treatment covariance, the treatment is as if randomized. So those who were from the control group can be representative of Y0 for those who are assigned to the control group. So in this case, you are able to satisfy this first part of ignorability assumption. And it also includes the positivity assumption. In other words, within levels of pre-treatment covariance, every individual has a non-zero probability of receiving each treatment level. This part is a very straightforward extension of the identification assumption for the total treatment effect. And the second component is new, which is strong ignorability of the mediator. That means there's no unmeasured pre-treatment confounder and no post-treatment confounder of the mediator outcome relationship. So here I mentioned the pre-treatment confounder and the post-treatment confounder. I'll illustrate those later. By pre-treatment, I mean before the treatment. By post-treatment, I mean after the treatment. If you think about this carefully, you may notice that the confounders of the mediator outcome relationship may occur before the treatment and may also occur after the treatment. If before, it's called pre-treatment. If after, it's called post-treatment. And in this course, we assume that there are no unmeasured pre-treatment confounders and there are no post-treatment confounders at all. In other words, the mediator is as if randomized within the same treatment group or across treatment groups among individuals with the same levels of pre-treatment covariance. It's a very straightforward extension of the strong ignorability of the treatment. We replace the treatment with the mediator. But for the confounders of the mediator outcome relationship, it's more complex because the confounders may happen before the treatment or after the treatment. And we also assume positivity assumption. In other words, within levels of pre-treatment covariance, every individual has a non-zero probability of taking each mediator value within all of the possible values of the mediator under each treatment condition. Discussions around the positivity assumption are very limited in the literature of causal mediation analysis. And you may imagine that when the mediator is continuous, this may be violated. Well, when the mediator is binary, usually this assumption is easier to hold. So as you may notice that in the causal world, we have different assumptions. The first set of assumptions is for the definition of the potential outcomes. And the second set of assumptions here are for identification. And later on, we're gonna discuss and introduce sensitivity analysis for assessing the influence of violations of such assumptions. This is actually very important for a causal analysis because in the real world, these assumptions can rarely hold. It's highly likely that you omit some confounders from the analysis arbitrarily because you don't have enough power, or you in the data collection stage you didn't measure some confounders. It's all possible. So you cannot say that these assumptions hold. Usually these assumptions do not hold. And your an important task is to assess whether your results are sensitive to violations of such assumptions. So I want to draw your attention to the importance of sensitivity analysis later. For now, let's just discuss the assumptions. As we mentioned earlier, a variable that affects both the mediator and the outcome is known as a confounder of the mediator-outcome relationship, as represented by the yellow part here. In the news example, a mother who was less willing to accept a low-wage job might be less likely to be employed and tend to experience more depression if assigned to LFA. Therefore, the observed association between employment and depression might be partly attributable to the confounding of the willingness to accept a low-wage job. Failures to adjust for such confounders in the analysis would generate bias. It's possible that the confounder of the mediator-outcome relationship may be affected by the treatment as represented by this error, as we just discussed. This is called post-treatment confounder. And the identification of the indirect direct effects requires a strong assumption that there is no post-treatment confounders. And later on, actually, I provided a reference on how to relax such assumption through a sensitivity analysis. In this example, treatment is randomized. Therefore, there's no arrow from X to T. So that means there is no confounder of the treatment mediator or treatment outcome relationship. Therefore, the ignorability of the treatment is guaranteed. However, if the treatment is not randomized, there will be confounders of the treatment mediator and treatment outcome relationships. Omitting these confounders would also lead to bias. Therefore, it is important to include such confounders in the analysis. Otherwise, causal conclusions regarding the mediation mechanisms would be invalid. And as I mentioned, you should also conduct a sensitivity analysis to assess the influence of unmeasured confounders. Any questions? Okay. So far, we have discussed the assumptions, and relying on these assumptions, we can identify the effects through regressions. And path analysis models, as we introduced earlier, include a mediator model and an outcome model, but they assume no treatment by mediator interaction TM, and usually do not adjust for pre-treatment covariance X. If you go back to the earlier slides on path analysis, you will notice that in the mediator model, we only regress the mediator on the treatment without controlling for X. And in the outcome models, we also didn't control for X, and we also didn't have the treatment by mediator interaction term. And Vanderwill and Van Stelen relax these assumptions by further adjusting for the interaction and the pre-treatment covariance. So if the mediator and outcome are continuous, we have the new mediator model as this. So we further add the covariance X. And if you compare the outcome model to the earlier outcome model in the path analysis, you will notice that we further add the TM interaction and X. X here are the pre-treatment covariates. Under the sequential ignorability assumption in the above model-based assumptions, we can identify the population average of each potential outcome as this. And here, if you replace T and T prime both with 1, you will get the population average of Y1 M1. And also you can get the population average of Y0 M0 and the population average of Y1 M0, so that you will be able to get that NIE equals this and NDE equals this. Here I use NIE and NDE as illustration. Using the same logic, you can derive PIE and TDE. Now, you can tell how the definitions of NIE and NDE change after accounting for confounders and treatment by mediator interaction. Remember earlier when we used the path analysis models that do not have TM interaction and the covariance X, the indirect effect is simply defined as the product of TM path and MY path. But now it becomes more complex as we further include an interaction effect. And for NDE, it becomes way more complex as earlier when we discussed the traditional path analysis. Remember, the NDE is defined as simple as the path from M to Y. But now it gets more complex. So this slide completes the whole section on causal mediation analysis. Through this section, I hope you can have a better idea about the definition, identification, and estimation. So we use these models to estimate the indirect and direct effects. What we do is that we get the estimates of the regression coefficients and replace them here so that we can get the estimates of NIE and NDE. So we begin from the definition, which relies on unobservable quantities. And in order to relate the unobservable quantities to observed data, we identify the effects under the sequential ignorability assumption, based on which we identify the effects and then we estimate them through regressions by extending the traditional path analysis models that ignore the treatment by mediator interaction and the pre-treatment covariates. Usually. Any questions so far? If not, then we're going to move on to the next section on causal moderated mediation analysis. This section is actually a very straightforward extension of the previous section. Again, let's begin from the definition. Remember how we define the population average mediation effects? We define the individual specific effects first, and then we take an average of the individual specific effects over all of the individuals so that we are able to define the population average effects. But now we're going to define the causal moderated mediation effects. How to define the moderated mediation effects? By moderated, we mean we want to take a contrast of the conditional effects between two different levels of the moderators. So we want to begin from the definition of the conditional effects and then take a contrast. Then how to define the conditional effects? It follows the same logic when we as the definition of the population average effects. We simply average each individual specific effect over individuals within given levels of the moderators so that we are able to define the conditional average of each effect as this. Remember earlier when we defined the population average effects, we just take an expectation of the individual specific effect. Here we denote it as delta I. But now we introduce moderators. So we have it as the condition here. We take a conditional expectation of the individual specific effects at given levels of the moderators, so that each moderated effect can be defined as a contrast of the conditional effect between subpopulations defined by different levels of the moderators, like this. So here we use delta to define the total effect, the total indirect effect, pure direct effect, pure indirect effect, and total direct effect, any causal mediation effect. And these definitions intuitively formalize mediation moderation without relying on any statistical models and apply to all the possible moderated mediation scenarios. Remember earlier when I mentioned the limitations of the traditional moderated mediation effects. So one limitation is that they don't have a general definition. The definitions rely on specific models. But here, under the potential outcomes framework, we can offer general definitions without relying on any specific models. You simply define the individual specific potential outcomes and correspondingly the individual specific indirect direct effects. And then you take the conditional expectation of each individual specific effects, which will give you the definition of the conditional effects. And by taking a contrast of the conditional effects, you are able to define the moderated effects. Any questions? So now after the definition, which relies on the unobservable quantities, we can move on to the section of identification, which relates the unobservable quantities to observed data. And the extension is again straightforward. We extend the assumption by further conditioning on the moderators. We assume that within levels of the moderators, strike nervability of the treatment holds. In other words, there's no unmeasured confounding of the treatment mediator or treatment outcome relationship. Within levels of pre-treatment covariates, every individual has a non-zero probability of receiving each treatment level. That means within levels of pre-treatment covariates, some individuals were in the control group and some individuals were in the intervention group. We cannot have a case in which all of the individuals were in the same group. Otherwise, we are not able to provide counterfactual information for the other group, right? And we also assume strong ignorability of the mediator. In other words, there is no unmeasured pre-treatment confounding and no post-treatment confounding of the mediator outcome relationship. As emphasized earlier, the confounder of the mediator outcome relationship may occur before or after the treatment. We call pre-treatment and post-treatment, and we assume no post-treatment, which is a strong assumption. Because in many real applications, it's possible that the confounder of the mediator outcome relationship occur after the treatment. In our example, for example, one's willingness to get a job may be affected by the treatment, which further confound the relationship between the mediator and outcome. This will become a post-treatment confounder. But in this case, we have to assume that there's no such post-treatment confounder. So this is a very important topic that is being discussed in the literature of causal mediation analysis. My colleagues and I developed sensitivity analysis strategy to relax this assumption and other researchers propose causal mediation analysis methods under an alternative interventional framework. But these are not within the scope of this workshop. I mentioned this mainly for your future reference. Knowing the limitations of the methods is important for you to further refine your discussion section in your paper. Within levels of pre-treatment covariance, every individual has a non-zero probability of taking each mediator value within all of the possible values of the mediator under each treatment condition. If this is violated, that means you're not able to provide the counterfactual information of the mediator under the other group, then there'll be a problem, as we discussed earlier. But in the current causal mediation analysis literature, very, very few discussions have been focused on assessing the violation of this assumption. But this assumption may also be violated. So these are something that you may want to consider discussing in the discussion section of your paper, by thinking about your real example, whether these assumptions are violated. Any questions? And another question you may have after reading the materials more deeply, you may question whether a moderator can be a confounder as well. The answer is yes, a moderator may or may not be a confounder. If a moderator is a confounder, then these assumptions are equivalent to strike nervally that we mentioned before. But sometimes the moderators may just be moderators that of a theoretical interest, but they do not confound any relationships. It's possible. Any questions? So now, in order to estimate the effects, again, we focus on regression here. Here are the models that we use for the estimation of the indirect direct effects, as we introduced earlier under the section of causal mediation analysis. To further assess moderated mediation, we can incorporate pre-treatment moderators in the models. And the model specification and interpretation would become increasingly challenging as more moderated relationships are considered. Well, such concerns can be greatly alleviated if we specify the models in a hierarchical form. So based on these main models, we can further express each coefficient as a function of the moderator W. For example, beta Tm here indicates the path from the treatment to the mediator. And I write this beta Tm as a function of the moderator so that beta Twm indicates how W moderates that path. And similarly, this beta Ty indicates the Ty path, while beta Twy indicates how W moderates that path from T to Y. For illustration purpose, we focus on one single moderator here and include the moderator in the models of all the main model coefficients. The models can include more than one moderators in reality, and the moderators do not need to be included in the models of all the main model coefficients. It can be very flexible. We're going to discuss the specification of the models in the last section on our implementation. And the models can be alternatively written in a combined form, which you may be more familiar. But if you combine this combined form to the hierarchical form, you may notice that the hierarchical form facilitates the specification and interpretation of moderation. So based on your theoretical reasoning, you may have an idea about which path the moderator moderates, based on which you are able to write out the hierarchical form in an easier way, while the combined form is more difficult to specify. And the models can be fitted with bootstrapping method, Monte Carlo method, or Bayesian method. Follow the same logic as the earlier one of the earlier slides. At I think it's the last slide of the causal mediation analysis section, we can estimate the conditional and moderated indirect and direct effects based on these model-based assumptions. And more details can be found in Qin and Wang paper that I sent earlier. Any questions? So now we've finished the section on causal moderated mediation analysis, which is actually a straightforward extension of the causal mediation analysis section. It again follows the idea of definition, identification, and estimation. And the major difference between the models in this slide and the traditional moderated mediation analysis is that we further account for the treatment by mediator interaction, which is usually ignored in traditional mediation analysis. But in reality, we all know that mediator may transmit the impact of the treatment on the outcome by interacting with the treatment. So it's important to include the treatment by mediator interaction. But you may notice that after including the treatment by mediator interaction, it greatly complicates the definition of the indirect and direct effects, as we illustrated earlier. But I want to take this opportunity to draw your attention to the importance of including such an interaction between the treatment and the mediator in the outcome. And also, it's very important to control for the confounders, the X, in the mediator and outcome models. It's incorrect to omit them from the mediator and outcome models. Additionally, it's extremely important to conduct a sensitivity analysis in your analysis. So I want to step on to the next section, sensitivity analysis. So any question about the earlier discussions on the mediation and moderated mediation analysis under the potential outcomes causal framework? Okay. So this is another very important section. I want to begin this section with the motivation. Why is sensitivity analysis essential? As we emphasized earlier, the identification strategies rely on the sequential ignorability assumption. The strong ignorability of the treatment is guaranteed by random treatment assignment. The strong ignorability of the mediator would be violated if there was an omitted pre-treatment confounder or a post-treatment confounder of the mediator-outcome relationship. For example, as we illustrated earlier, among the participants with the same welfare amount and number of children prior to randomization, those who are less willing to accept a low-wage job before participating in the study, or in the first year after participation, which are respectively the pre-treatment and post-treatment confounder, might be less likely to be employed in the 2 years after participation and tend to experience more depression at the end of the second year, especially if assigned to the LFA program. So in this example, I want to illustrate that in our real example, there may be a pre-treatment confounder or a post-treatment confounder of the mediated outcome relationship. In this case, a sensitivity analysis is necessary for determining the influence of a potential omitted confounder or how strong omitted confounding needs to be for the sign or statistical significance of the original conclusions to be changed. Because as we mentioned earlier, when you have a confounder, but you omit it from the analysis, this would generate bias in the direct and indirect effects. But sometimes the bias may be very minor. It may not change the sign or statistical significance or the magnitude of the original results too much. So it's fine to omit them. But sometimes there may be very important confounders. You cannot omit them from the analysis. Omitting them from the analysis would generate large bias and cause the change in the sign and or the statistical significance of the original conclusion, or it may lead to a change, a lot of change in the magnitude of the effect estimates. That would be problematic, and the results would be sensitive to such unmeasured confounders, which needs to so people cannot ignore this. Therefore, it is very important to conduct a sensitivity analysis to assess the influence of unmeasured confounding. So hopefully this will draw your attention to the importance of sensitivity analysis. And then we're going to introduce some basic ideas of sensitivity analysis. If a confounder is observed but arbitrarily omitted from the analysis, then we can simply compare the results before and after including the omitted variables in the analysis. You may question when we arbitrarily omit a confounder from the analysis. This is the case usually when we have limited sample size. We do not want to include all of the covariates in the model, and we want to avoid overfitting. So we try to omit some observed covariates from the analysis. But if you argue that this may be an important confounder, omitting it may change the results a lot, then you just want to compare the result before and after including such observed variables. And the tricky thing is that if a confounder is unmeasured, what shall we do? Then we can use sensitivity parameters to imply departures from the identification assumptions due to unmeasured confounding. In other words, the sensitivity parameters reflect the strength of unmeasured confounding. The stronger the unmeasured confounding is, the stronger sensitivity parameters are, the stronger the departure from the identification assumptions would be. Then we assess point estimates of the indirect and direct effects and their standard errors as functions of the sensitivity parameters. And that means through this step, we're able to tell how the estimates and standard errors of the indirect direct effects change when the unmeasured confounding gets stronger or it gets weaker. And the larger the magnitudes of the sensitivity parameters are for removing the effects or changing their significance, the less sensitivity the results are. What does this mean? When the magnitudes of the sensitivity parameters are larger, that means the unmeasured confounding is stronger. So when the effects are removed, that means when the effects are removed or their significance are changed. And so in order to remove the effect or changing their significance, the unmeasured confounding have to be very strong. Otherwise, the results would not change much. That means the results are robust. But if the results can be changed a lot when the sensitivity parameters are very small, that means even a very weak unmeasured confounder can change your original results dramatically. That means your results are sensitive to unmeasured confounding. I hope this makes sense to you all. Any questions? So I want to add that this section is focused on assessing the influence of unmeasured pre-treatment confounding. A discussion on post-treatment confounding can be found. I think the slide numbers change slightly. I can update the slides after this workshop. We can reduce the possibility of post-treatment confounding by choosing the time point of measurement for the mediator to be relatively close to that for the treatment. That means when the treatment and the mediator are measured relatively closely, then there is less chance that the confounder of the mediator outcome relationship occur on the path from the treatment to the mediator, because the treatment mediator are measured relatively closely. So there is a less chance of a post-treatment confounder of the mediator outcome relationship. So this can be done at the data collection stage. And another solution is to adjust for post-treatment confounding through a sensitivity analysis strategy or from an interventional perspective. More details can be found on those slides. So now, with the focus on pre-treatment confounding, let's take a look at the basic idea of the simulation-based sensitivity analysis method. So the goal of this study is to understand what the estimates of NIE and NDE, the natural indirect direct effects, and their standard errors would have been had we adjusted for an unmeasured pre-treatment confounder. Here we use U to denote a confounder. So originally in this diagram, we only have X, but here we notice that there may be a U that is unmeasured. So for the identification assumptions to hold, we have an additional U in addition to X. So knowing that the goal of the study is to understand what the estimates of NIE and NDE and their standard errors would have been had we adjusted for an unmeasured pre-treatment confounder U, we realized that if we can adjust for this U in the analysis, then the problem will be solved. But the problem is that U is unmeasured. How can we further adjust for this U in the analysis? To reach this goal, our solution is to derive a conditional distribution of U based on our assumptions about its prior distribution and its relationship with the outcome and the mediator. That means knowing how strong this unmeasured U is associated with the outcome and the mediator, we can derive its conditional distribution so that we can draw it from its conditional distribution. Then we're able to adjust for it in the analysis. And then we can estimate NIE and NDE after the adjustment for U. That's the idea. The idea is very similar to the first one, if a confounder is observed. So if a confounder is observed but arbitrarily omitted from the analysis, then we can compare the results before and after including the omitted variables in the analysis. This can be easily done because the confounder is observed. But if the confounder is unobserved, we can derive its conditional distribution and randomly draw it from its conditional distribution. And to account for its uncertainty, we can repeatedly draw it from the analysis and adjust for this multiple draws, the uncertainty. Then we can compare the results before and after, including the unmeasured confounder in the analysis, so that we can assess the sensitivity of the results. So the idea actually is the same as this case, but the essence of the method is to derive the conditional distribution of U based on the strength of unmeasured confounding. And the results can be visualized through this plot. Here, the X and Y axis are the sensitivity parameters, which are the slopes of unmeasured confounder in the standardized mediator and outcome models. And each black contour represents the combinations of sensitivity parameters that lead to the same effect estimate as indicated by the number on the contour. I see a hand raising, Faye. Yeah, feel free to ask your question. I think you're muted. Is that right? You have a question? Yeah, I cannot hear you for now. I can hear echo. Yeah, if you have any question but have trouble then you can type in your questions in the chat window. Here I want to add that if an unmeasured so I want to say more things about the second bullet point. Each black contour represents the combinations of sensitivity parameters that lead to the same effect estimate as indicated by the number on the contour. So let's just focus on this one single contour. Let's just focus on this one single contour. What does it mean? For example, if the standardized partial effect of U on the latent index of M, because here M is a binary variable, is 0.2. While Y-axis is also 0.2. Then what we do is that with the two given sensitivity parameter values, we derive the conditional distribution of U. Then we randomly draw U from its conditional distribution and adjust for it in the causal mediation analysis. And then we get that the adjusted pure indirect effect estimate is -0.2. And similarly, when the x-axis is 0.4 and the y-axis is around 0.1, we get another conditional distribution of U and draw U from it. We get that the adjusted effect estimate is also -0.2. Then we connect all of the dots at which the adjusted effect estimates are -0.2 so that we can get this contour. And similarly, we can get all the other contours here. I hope this illustration helps you have a better idea about the second bullet point. That is, each black contour represents the combinations of sensitivity parameters that lead to the same effect estimate as indicated by the number on the contour. The number on the contour represents the effect estimate with adjustment for the unmeasured confounder at the corresponding sensitivity parameter values along the contour. And the sensitivity parameters along the red dashed contours reduce the effect to 0. That means when the sensitivity parameters take the values on those red contours, then the effect with adjustment for such unmeasured confounders becomes 0. So the original effect estimate is negative 0.016. So on this side, within this area of the 0 contours, the effects are negative, but outside this red region, you will get the positive effect estimates. This indicates the boundaries at which the sign of the effects changed. While each blue dotted curve corresponds to the boundary at which the significance of the effect is changed. And the effect is insignificant on the side that contains the 0 line. That means on this side, in this region, within these blue dotted contours, the effects are insignificant. While outside the blue boundaries, you will get significant results. Now, let's try to recall the basic idea of sensitivity analysis that we mentioned. When are the results sensitive? The results would be sensitive if even a very weak unmeasured confounder can change the sign or the significance of the original conclusion. And if for the sign or significance of the original conclusion to change, the unmeasured confounder has to be very strong. That means the results would be robust to unmeasured confounding, right? So the larger the magnitudes of the sensitivity parameters are for removing the effects or changing their significance, the less sensitive the results are. Now let's take a look at the chat window. Okay, making sure that there's no question. So this is the idea of sensitivity analysis and how to read the sensitivity plot. It's very important to understand how to read this plot because I'm going to show you how to implement the sensitivity analysis in R later. Now, I have introduced the black, red, and blue contours. And what about those dots? Each dot corresponds to the conditional associations of each observed covariate with the outcome in the mediator, which are used to calibrate the strength of the sensitivity parameters. And the plot shows that an additional adjustment of an unmeasured pre-treatment confounder U would reverse the sign of the pure indirect effect as long as the confounding rule of U is as strong as one's baseline educational attainment or work preference. So here, I didn't show it out. I show it here. So after running the analysis in R, R will tell you what those dots are. 1 to 7 are respectively comparable to prior employment status, and the other covariates, those are the covariable variable names in your data. And from this plot, you can clearly see that I'm going to circle the corresponding dots here. This is dot 5 and this is dot 4. These are respectively one's baseline educational attainment and work preference. As you can see that if an unmeasured confounder is comparable to either one of these two predetermined covariates, then the sign of PIE can be reversed. What does that mean? That means the results may be sensitive because an unmeasured confounder that is comparable to educational attainment or work preference can be easily found. Nevertheless, for the significance of PIE to be altered, you must be much stronger than the strongest observed predetermined confounder because the boundary of the significance change is further away from those unmeasured confounders that are comparable to the observed covariates. Because we can argue that we have controlled for the most important predetermined confounders in theory, it is almost impossible for the remaining confounders to reverse the significance of PIE, even collectively. Therefore, the sign of PIE may be sensitive. If we can find a measured confounder that is comparable to those observed covariates, then the sign can be easily reversed, but the significance is more robust. Similarly, should there be a set of potential unmeasured predetermined confounders, one could evaluate their collective influence by comparing their joint confounding role to the observed covariates. And in this slide, I want to further emphasize the essence of the plot. The further away the red and blue contours are from the black dots, the less sensitive the results are to potential unmeasured predetermined confounding. So this sentence emphasizes how to read this plot. To determine if your results are sensitive or not, you just try to see how far away the red contour, which indicates the change of the sign, the boundary of the change of the sign, and the blue dotted contours, which are the boundaries of the significance change, just to see how these red and blue contours, how far they are away from the black dots, which indicate the unmeasured confounders that are comparable to observed covariates. If they are further away from the observed dots, that means in order to reverse the sign or the significance change, your unmeasured confounder have to be much stronger than the observed covariates. And if you can argue that we have already controlled for the most important confounders in theory, then you can conclude that the results are robust. And so here I just arbitrarily manipulate the plot to give you the idea. So originally we concluded that the significance is robust, but because the red lines are so close to the black dots, the sign is not robust, it's sensitive to unmeasured confounding. But if in this case, the red contours are further away from the observed covariates, then the sign would be more robust. I hope these discussions help you have a better understanding about how to read the sensitivity analysis plot, because sensitivity analysis is a very important part of a causal analysis. I want to draw your attention to it, and it may require some time to digest all of the content. So I strongly encourage you to read the materials that I shared after this workshop if you find the materials helpful. Any questions? Okay, So far, we have already finished introducing all of the fundamental knowledge for causal mediation and causal moderated mediation analysis, including the definition, identification, regression-based estimation by extending path analysis models, and sensitivity analysis. In our last section, we're gonna learn how to implement the analysis in R. And you will have some time to do the exercises to make sure that you have understood how to implement the analysis. We have developed the R package moderate.mediation for researchers to estimate and test the conditional and moderated mediation effects, assess sensitivity to unmeasured pre-treatment confounding, and visualize the results. The package is applicable to a treatment of any scale, a binary or continuous mediator, a binary or continuous outcome, and one or more moderators of any scale. You may find an introduction to the R implementation in my email. It is a web page on R implementation for causal moderated mediation analysis, which is the same as in the Jin and Wang 2024 paper. Now, let's review our hypothesized moderated mediation mechanism that I illustrated earlier. The treatment variable name is treat, and the mediator variable name is imp, and the outcome variable name is depression. And our moderators include ADCPC, which is baseline welfare amount, and CHCNT, which is the baseline number of children. And here ADCPC is continuous, while CHCNT is discrete because one indicates one kid, two for two kids, and three for three or more kids. And we specify the models in the hierarchical form. We begin from the mediator model. In the mediator model, we regress the mediator on the treatment and the covariates. And so that the path from the treatment to the mediator in this hypothesized diagram mediation mechanism can be captured by the coefficient of the treatment in the mediator model. And then we have the outcome model, which regresses the outcome on the treatment mediator, the treatment by mediator interaction, and the covariates. And the path from the treatment to the outcome can be captured by the coefficient of the treatment in the outcome model, and the path from the mediator to the outcome can be captured by the coefficient of the mediator in the outcome model. And here we use an arrow from the treatment to the path from the mediator to the outcome to indicate the treatment by mediator interaction, which means that the mediator affects the outcome differently between the treatment conditions. And we use an arrow from the mediators, from the moderators to the path from the treatment to the mediator to indicate that the treatment mediator relationship is moderated, which can be moderated as this. So here I want to model that the path from the treatment to the mediator is moderated. So the coefficient of the treatment in the mediator model can be written as a function of the moderators. And the notations here change slightly compared to those in the previous models, because here in this example, we have two moderators. Well, earlier when we used the hierarchical form to illustrate the moderated mediation regression, we only have one moderator. So the notations change a bit. We use both W to denote a vector of two moderators here. And you might have learned from regression courses that every variable involved in the interaction term should also have their own main effects. Therefore, in addition to write the coefficient of the treatment in the mediator model as a function of the moderator, we should also write the intercept as a function of the moderators, and the coefficients of the moderators here represent their main effects. And similarly, we write the coefficient of the mediator in the outcome model as a function of the moderators to reflect that the path from the mediator to the outcome, is also moderated by the moderators. So these are based on the theoretical reasoning. Theoretically, I argue that the relationship between the employment and depression may depend on the baseline welfare amount and number of children. That's why I write the coefficient of the mediator in the outcome model as a function of the moderators. Similarly, I argue that the path from the T to M, from the treatment to the outcome, is also moderated. And again, as I emphasized earlier, when you have the interactions, you should also write the intercept as a function of the moderators. So that's why I have this. In addition, I also argue that the treatment by mediator interaction may also be moderated. So that's why I have the moderators to interact with the coefficient of T in the mediator model, and also with the coefficients of Tm and Tm interaction in the outcome model. This finishes the specification of the regressions in the hierarchical form. As you can see that the specification of the model relies on theoretical reasoning. And as you may know, the regression-based analysis relies on the model-based assumptions. So this can be another limitation that you may want to discuss in the discussion section. If the models are specified in the wrong way or incorrectly, then the results may also be biased. And you may argue that theoretically we believe that these paths are moderated by those theoretically important moderators. That's why we model the mediator and outcome models in this way. So, any questions so far? I try to illustrate how I think through this process, and then let's see how to implement or how to specify the models in R. And after installing the package, you can call the data news by running data parenthesis news. And then you can use the modmed function, MODMED. And first of all, you tell the program your data name and your treatment variable name, your mediator variable name, and your outcome variable name, and the name of your discrete covariates, the name of your continuous covariates. You tell the program the discrete and continuous covariates names separately. In this way, you're not you do not need to factorize the discrete covariates on your own. You only need to tell the program what which covariates are discrete and which covariates are continuous, and then the program will factorize the discrete variables for you. You do not need to worry about that. And then similarly, you tell the program what are the discrete moderator names and what are the continuous moderator names. Here we only have one discrete moderator and one continuous moderator, but if you have a vector of discrete moderators or continuous moderators, then you have to write them as a vector, C parentheses as shown here. And for these covariates, disk covariates continuous, moderators disk and moderators continuous, their default values are null. So there's no need to specify moderators dot disk if there are no discrete moderators. And now is the time to specify the most important part, m dot model, the mediator model. You write it as a list. So now try to recall our mediator model. This is our mediator model that I showed earlier. This is the main model, and I write the intercept as a function of the moderators, which give the main effects of the moderators. And I also write the path from treatment to the mediator as a function of the moderators. So when specifying the mediator model, tell the program that the intercept is a function of the moderators, and the coefficient of the treatment in the mediator is also a function of the moderators. While for the other covariates, including employment prior, etc., these are not moderated, so they are equal to now. And similarly for the outcome model, remember, this is our main outcome model, and this is our function of the intercept indicating the main effects of the moderators. And also we have the coefficient of the treatment in the outcome model as a function of the moderators. So we write this. And also we have the coefficient of the mediator in the outcome model as a function of the moderators. I write it in this way. And also I specify the treatment by mediator interaction coefficient in the outcome model as a function of the moderators. So these are moderated, but for the covariates, they're not moderated, so they're equal to null. So this finishes the specification of the mediator and outcome models in the hierarchical form. And another thing you want to consider is that you need to tell the program which two treatment values are contrasted. We compare treatment 1 to treatment 0. And also you want to tell the program which two moderator values are constructed. For the discrete moderator, we compare those who had 3 or more children at baseline and those who only had 2 children at baseline. So the compare and reference moderator values are respectively equal to 3 and 2. And for the continuous moderator, we control it at its median, so that we want to see when the baseline welfare amount is at its median, what's the difference in the indirect effects between those who have 3 or more children and those who only had 2 children at baseline. If you do not want to condition some moderators on specific values, you may specify their values to be NA. That means if you want to just compare those who have 3 children at baseline and those who have 3 or more children at baseline and those who had 2 children at baseline, while not conditioning on any specific value of baseline welfare amount, then this 5050 can be replaced with NA. And the scale of the mediator is binary. The scale of the outcome is continuous. And the estimation method is Monte Carlo method. And these are the number of Monte Carlos, which is 1,000. And the confidence, the significance level is 0.05. So the confidence level is 0.95. And because this is based on the Monte Carlo method, you want to specify the number of seed. Otherwise, the results will change very slightly across different rounds. And after running this function, you can summarize the analysis results by running the summary function. And in the output, you will obtain the estimates of the population average effects, the conditional effects of the reference group, and the moderated effects. And you will also test the significance. And here I have a slide on how to interpret the results, which is mainly for your future reference. After obtaining the output, you will be able to tell that the total LFA effect is estimated to be 0.48, which can be decomposed into a pure direct effect, which is estimated to be 1.24, about 16% of a standard deviation of the outcome in the control group, and a total natural indirect effect estimated to be negative 0.76, about negative 9% or 10% of a standard deviation of the outcome in the control group. And the pure direct effect indicates that LFA would have increased maternal depression if one's employment experience is held at the level under the control condition, but not by a statistically significant amount. In contrast, the total indirect effect reflects that the LFA-induced increase in employment rate significantly reduced one's maternal depression when the treatment is held at the LFA condition. The counteracting indirect and direct effects explain the insignificant total effect. Through this example, you may also tell that sometimes even if the total effect is insignificant, it is still very interesting to further decompose the total effect, because as in this example, you can tell that the indirect effect is significant while the direct effect is not. So the significant indirect effect is very interesting, which tells that although the total effect is now, the employment actually plays a very important mediating role. And in order to improve the treatment effect, you may want to further improve one's employment rate through the intervention. And this can provide practitioners some guidance on how to improve the intervention. And as we mentioned earlier, for the total effect decomposition, I recommend one to decompose it into 3 components: the pure indirect direct effects and the interaction. Well, just now when I report the results, I decompose it into a pure direct effect and a total indirect effect. Here, a total indirect effect can be further decomposed into a pure indirect effect, which is estimated to be negative 0.02, and a natural treatment by mediator interaction effect, which is estimated to be negative 0.75. And the natural interaction effect indicates that LFA-induced increase in employment rate reduced maternal depression more under the LFA condition than under the control condition. Equivalently, the natural treatment by mediator interaction effect can also be viewed as the difference between the total direct effect and the pure direct effect, which indicates that LFA would have increased the maternal depression to a smaller extent if holding one's employment experience under the LFA condition than if holding that under the control condition. And you may ask that here, the interaction effect, although its magnitude is relatively large, it's insignificant. And I want to add here that in a mediation analysis, usually it requires a larger power to detect a significant interaction effect. I actually developed a power analysis Shiny app, and I also wrote a paper on that. And through my by reading my paper, you can see more clearly that a larger sample size is required for detecting a significant interaction effect at a given power. And the reference of the paper is also available on either my webpage or the end of the slides. And through the moderated mediation analysis, we further detected a significantly positive pure direct effect among those who had 2 children at baseline and received median level of welfare in the year prior to randomization. And I want to add here that you may notice that when reporting the results, I begin from the population average effects, and then I move on to the moderated effects. And this conditional pure direct effect, so I begin from the conditional effect and then talk about the moderated effect. This conditional pure direct effect is significantly higher than that of those with 3 children and the median welfare in the year prior to randomization. The magnitude of the difference is estimated to be 3.75 of the 71, which is significant. So this finishes the running of the program and the reporting of the results. And I hope through this illustration, you will have a better understanding about how to run the analysis in R and how to summarize the results. And now you're gonna have several minutes to do the exercise. And we're gonna use jobs 2 data. Jobs 2 is a randomized field experiment that investigates the efficacy of a job training intervention on unemployed workers. The program is designed to not only increase reemployment among the unemployed, but also enhance the mental health of the job seekers. You should have received the data in my email. In the Jobs 2 field experiment, almost 2,000 unemployed workers received a pre-screening questionnaire and were then randomly assigned to treatment and control groups. Those in the treatment group participated in job skills workshops. In the workshops, respondents learned job search skills and coping strategies for dealing with setbacks in the job search process. Those in the control condition received a booklet describing job search tips. In the follow-up interviews, continuous measures of job search efficacy and depressive symptoms were sequentially measured. So I would like you to import the dataset by running the following code in R. And the folder where I save the data is a drive in a folder named R, and you may save them under a different path. You just replace the path name here, and just try to remember you use these 2 double slash, or you can do 1 single slash on this opposite way. And the treatment variable name is treat. Mediator is job seek, which is the level of job self-efficacy with values from 1 to 5. And the outcome is depressed 2, which is the measure of depressive symptoms post-treatment. And moderator is econ heart. And pre-treatment covariates include depressed at baseline, sex, and age. And the hypothesized diagram is like this. Now you want to conduct the moderated mediation analysis based on the above diagram using the mod-med function, and you want to report the estimation and inference results of the total indirect effect among those whose econ heart is equal to 1, and the difference in the total indirect effect between those whose econ heart is equal to 5 and those whose econ heart is equal to 1. And this is the exercise. In order to save your time, I have already written out the other parts. I have already written out the data name and the variable names. And your job is to fill out the mediator model and the outcome model and the comparison and reference values of the continuous moderator econ hard. And I'll give you 5 minutes. What you want to do is to download the data set that I emailed you earlier, and then open the R code with the name exercise or exercises, and then you can run the code and then fill out the mediator and outcome model and those two values of the comparison and reference moderators, and then see if you can get the results. I'll give you 5 minutes to finish this exercise, and then I'll show you the solution on the next slide. Please let us know if you have any trouble downloading the data set. This is actually the exercises R code that I mentioned. So what you want to do is that you install the package and then run library function, import the data set, try to make sure replace this path with the path of the folder where you save the data, and then you complete these 2 lines and these 2 lines. And when specifying the mediator and outcome models, you may want to refer to this slide. You just tell the program that the intercept is a function of the moderator, treatment is a function of the moderator, and theoretically speaking here, in my example, I argue that the covariance coefficients are not moderated, so they're equal to now. And then the outcome model is specified in a similar way.
I have a question.
Sure.
In the first, in the R code, like the section import the data, should it be like read.csv instead of write?
Oh, yeah, that's right. Thank you for.
Thank you.
Yeah. Does everything go? Any questions? If you have not finished the exercise, don't worry. You can try it after the workshop. And now I would like to show you the solution very briefly so that we can check whether your answer is right if you have already finished the exercise. It's actually straightforward here. I assume that the coefficients of the covariates are not moderated, and the coefficient of the treatment in the mediator model is moderated. Because we also have to include the main effects of the moderator. So I write the intercept as a function of the moderator as well. And it's similar for the outcome model. Because as I mentioned earlier, I want to contrast the conditional effects between those whose econ hard is equal to 5 with those and those whose econ hard is equal to 1. So here I specify the moderator values as these. And after running these results, we can get the output, including the estimation and inference results of the population average effects and conditional effects and the moderated effects. So this completes the main analysis. But as I mentioned earlier, in addition to estimating and testing the effects, it's also very important to conduct a sensitivity analysis to assess the influence of unmeasured confounding of your results. Therefore, I also include the sensitivity analysis in the R package. And here you run the function named as modmet.sense. And first of all, you tell the program the name of the original results, which is results. Remember earlier, I saved the modmet results as results. And now you tell the program it's I want to conduct the sensitivity analysis for the original results named as results. And here, sense.effect is a vector of the effects for which you want to assess the sensitivity. And it can be specified as this full vector, including all of the effects, including the population average effects, the reference, the conditional effects of the reference group, and the difference in the effects between the comparison group and the reference group. And this can be specified as subvector of the default. This is the default, and it can be a subvector. It does not matter how the effects are ordered. And you can also tell the program the range of the x-axis and the y-axis. If you have not a specific idea, you can just specify them as now. These are default values. You can also do not write them. By default, the programs will actually generate the default x and y-axis values for you. And this is the grade numbers. So the idea of this generation of the plot is that it after you give the range of the x, y axis, you divide them into a 10 by 10 grid. For example, here 10 by 10, and then the program will estimate the adjusted effects at each given value of the sensitivity parameter on this grid. So the finer the grid is, that means the number, the larger the numbers are, the finer the grid is, so the smoother the contours would be. And by default, the scale of the unmeasured confounder is binary. Remember, I mentioned that you generate a U from its conditional distribution. So you should assume its scale. It can be a binary unmeasured confounder. It may also be a continuous unmeasured confounder, and sometimes it may be a collective set of all of the unmeasured of multiple unmeasured confounders. So it's not necessarily binary. Therefore, if it is binary, you specify it to be binary. But it can also be continuous. If it is continuous, then you should change U dot scale to continuous. If it is binary, you tell the program what is the marginal probability of the unmeasured confounder is. You can change it and see how the results would vary. And these can be specified based on your theoretical reasoning. So theoretically, if a very important unmeasured confounder is binary, you just specify it to be binary. But if you argue that there can be multiple unmeasured confounders, then it may be safer to specify it to be continuous. And by default, the program actually generated a standardized, a standard normal unmeasured confounder. Just the distribution of the unmeasured confounder is specified to be normal. And here, in our case, the treatment is randomized, but in some of your real examples, the treatment may not be randomized, and therefore there can be a measured confounder of the treatment mediator or treatment outcome relationship as well. In that case, you have to specify a treatment model because this treatment model is not needed for the mediation analysis. However, it is necessary for the derivation of the conditional distribution of U. Therefore, you want to specify the relationship between the treatment and the unmeasured and the covariates. I actually have an example in the paper. So if you're particularly interested in how to specify this T-dot model, and you want to check the paper or the R implementation R markdown page that I shared, and this B dot T is the sensitivity parameter that reflects the relationship between the unmeasured confounder and the treatment. And here you have the number of iterations, number of simulations that are needed for the sensitivity analysis. More details can be found in the paper in the R markdown page for our implementation as well. And because the sensitivity analysis requires intensive computation, so I incorporate this parallel computing to save more time. So here there are more details about introduction to the T.RAN, T.model, T.scale, B.T that I mentioned earlier. And if you're particularly interested in this, you can refer to the slide, and more details can be found in the paper in our markdown page. And to get the sensitivity analysis results, to visualize the results, you run the function sense.plot. You tell the program what is the name of the original results, what is the name of the sensitivity analysis results, and then you check the plot for each effect one at a time. And here I particularly interested in the sensitivity plot for the indirect effect. So I get the plot here. I actually have already talked about this plot earlier. Now I give the interpretation of the results here, again, mainly for your future reference. We can quickly go over it now. The figure shows that an additional adjustment of a binary unmeasured pre-treatment confounder U with the probability of being 0.5 would reverse the sign of PIE as long as the confounding rule of U is as strong as one's baseline educational attainment or work preference, as I explicated earlier. Nevertheless, for the significance of PIE to be altered, the unmeasured confounder must be much stronger than the strongest observed Friedman confounder. Because we have controlled for the most important Friedman confounders in theory, it is almost impossible for the remaining confounders to reverse the significance of PIE, even collectively. Therefore, the sign of PIE may be sensitive, but its significance is more robust. Similarly, we can obtain the sensitivity plots for the other effects, which are mostly robust to unmeasured pre-treatment confounding. Any question about this part? If not, we're going to move on to the exercise. We want to conduct a sensitivity analysis to evaluate whether TIE.ref and TIE.diff are sensitive to a potential violation of the identification assumption by completing the following code. For illustration purpose, please specify the grid numbers to be 2. Their values need to be increased in real data analysis. So here, you simply need to tell the program what's the name of the original results. It depends on what name you gave to your original results when you finished exercise 1. And tell the program which 2 effects you want to evaluate there, for which you want to evaluate the sensitivity. As I mentioned here, these 2 effects, we are particularly interested in whether these 2 effects are sensitive. So you just simply put these 2 effects here. And then the grid numbers, as I said, to speed up the running, you specify small grid numbers. And here I want to add that in your real applications, you may want to start with relatively small grid numbers to get the rough plots at the very beginning, and then try to refine the plot by increasing the grid numbers. And usually we don't recommend 2 because that's too small. You will just get some just the straight lines. You will not get a smooth contours. My suggestion in my paper is that these grid numbers can be start from 5, and then you can increase them to 10 to smooth them and report them in your final paper. And here in core, it depends on how many cores you have on your computer. For example, my computer has 8 cores. I usually specify them to be 7 because I want to have 1 more core to work on other stuff. And then you generate the sensitivity plot. As I mentioned, a plot is generated for 1 effect at a time. So you want to specify it to be TIE.ref 1 time, and then TIE.df for the other plot. Now you will have 3 minutes to work on the exercise, and I'll show you this slide to help you figure out how to know how many cores do you have on your computer. This function, detect cores, can be used to detect the total number of cores available on a computer. To use the function, you have to install and load the package parallel first. If you don't have this installed on your computer already, because it may take time, and you may just specify the detect cores equals 3 for safe. I think usually most computers has at least 4 cores, so you can specify it to be 3. I hope it went well. Now let's move on to yeah, the solution. In any trouble? The yellow parts are mainly for examining whether you have fully understood the major part of the exercise or of the programming. So if you have any confusions, please feel free to bring them up. If not, let's move on to the visualization of the results. So earlier we have finished the estimation and inference of the results or of the mediation effects, and then how to assess the sensitivity of the effects to unmeasured confounding. And then for moderated mediation analysis, a very important part is the visualization of the results so that you can see how the effects vary by the moderators. And so we use the function modmet.plot. You first tell the program what is the name of the original results, which is results, and which effect you want to look at. Here, I want to look at how the pure direct effect varies by the moderator. The effect can also be the TE, TIE, PD, etc. And moderator is the number of children at baseline. And other dot, so the other continuous moderator value is the median of the continuous moderator. If you do not want to condition some moderators on specific values, as I mentioned earlier, you can just specify their values to be NA. That's all. And more details about the specification of the function can be found in my paper in our Markdown page. Because the moderator here is categorical, so you will have this multiple box plots. And now, so this plot can be used together with the original output. Remember, in the output, you can tell the conditional effect when the number of children at baseline is 2. And then you can also tell the difference in the H effect between CHC and T equals 3 and CHC and T is equal to 2. And you can combine that output with this plot. Well, the interpretation of the numerical results is very important. Visualizing the results through the plot can tell readers the results in a more intuitive way, especially for practitioners who do not understand the idea of the methods. They want to tell the results in an easier way, then the visualization really helps. Now let's see how to interpret the results based on the plot. We can tell that among those who received the median welfare amount at baseline, the pure direct effect is estimated to be positive among those with 1 or 2 children at baseline, while significant only among those with 2 children. As you can see here, these are positive. What's the significant one is only this one, which does not contain 0, but these two both contain 0. In contrast, among those with 3 or more children, LFA would have reduced maternal depression if not changing one's employment experience, but not by a statistically significant amount. As you can see here, not by a significant amount. Well, the point estimate is negative. This matches and supplements the numerical summary obtained from the summary function. So that's why I said that you want to combine the numerical results with the visualized results. And now I also want to see how the effect varies by the continuous moderator. When the moderator is continuous, the function is specified in a different way. Here, the 5 percentile lines are added to the distribution of the moderator, which facilitates the evaluation of conditional effects at given percentiles of each continuous moderator, like this. So when the moderator is continuous, we'll get this smooth curve. And then based on the 5 percentiles, you can tell how much the effect is at a given percentile. And you can see this more clearly on this slide. Among those who had 2 children at baseline, the pure direct effect of LFA on maternal depression increased as one received more welfare amount in the year prior to randomization. The effect is significant only when the welfare amount is larger than $25,000, as indicated here. Because in this part, the band contains 0, while in this part, the band does not contain 0. So this is the significant area. This is the insignificant area. The sample distribution of the welfare amount indicates that about 70% of the participants with 2 children are in the significant region. In the last exercise, I would like you to visualize how the total indirect effect of the job training intervention on depression transmitted through job search self-efficacy varied by econ hard by completing the following code. You just tell the program the effect name. Here, I already let you know that I want to see the total indirect effect. And the moderator is econ hard. And because it takes time, you want to specify n core is equal to some number bigger than 1. Based on how many cores you have on your computer. This is actually a relatively easy exercise to finish because we only have 5 minutes now. I want some time to summarize what we have learned today. So we're gonna skip this exercise and you may just finish this in seconds by typing in TIE econ hard and this number of cores. While listening to the end of my workshop, you can run the program and see if you can get a plot in a couple of minutes. For those of you who have already finished the first 2 exercises, you can start running this function by filling in these blanks. And then we're going to move on. Here, I want to recommend the analytic procedure as follows. We recommend that researchers utilize the graphical tool for an overview of the influence of a moderator on the magnitude, sign, and significance of an effect. If the effect linearly changes with the continuous moderator, you can assess if the effect is significantly moderated by testing the difference in the effect between any 2 moderator values that are 1 unit apart because it's linear. So the difference between any 2 moderator values that are 1 unit apart actually applies to the whole real line. Otherwise, you can locally assess moderated mediation by testing the difference in the effect between 2 given values of the moderator, depending on your theoretical interest. So this is the overall recommendation of the analytic procedure. Hopefully through this workshop, you have already understood some foundational knowledge about causal mediation, causal moderated mediation analysis, including definition, identification, estimation, and sensitivity. In particular, I would like you to pay special attention to the importance of sensitivity analysis. And hopefully this R package provides you a tool to run such analysis. And I hope it can help with your real applications. And if you have any ideas about methodological development, I'm also happy to discuss with you further, and I'm happy to collaborate. And now in the last 1 minute, I would like to summarize the advantages and some limitations of the methods that we introduced in this course. By assessing how an intervention worked differently across individuals, we can better understand the intervention's efficacy and make individual-specific modifications of intervention design and implementation. Correspondingly, we can improve and tailor interventions to different individuals and therefore enhance educational equity. Specifying the models in the hierarchical form eases model specification and result interpretation. The visualization of the analysis results intuitively represents how a causal mediation effect varies by a moderator. A sensitivity analysis is incorporated to evaluate the sensitivity of the original results to potential unmeasured pre-treatment confounding. So the most importantly, I want you to fully understand why such a moderated mediation analysis is important. It's important because we want to better understand the intervention's efficacy and make individual-specific modifications. And lastly, I would like to briefly mention some limitations. The regression-based causal moderated mediation analysis method relies on correct model specification. We may fit non-parametric models or machine learning models to allow for more robust and flexible modeling, and the analysis assumes no post-treatment confounding. Here we focus on a pre-treatment confounding, a pre-treatment moderator. If a moderator is concurrent with the mediator, the estimation and inference stay the same, while the definitions and identification assumptions change. We actually mentioned that earlier. If a moderator is also a sequential mediator, we need to conduct a mediation analysis for sequential mediators that interact with each other. Extensions can be made for longitudinal or multi-level moderated mediation analysis or to account for measurement error. So these are the future directions. As you can tell that causal mediation analysis is a rising field. There are more and more methods developed. And so for social scientists in particular, I would like to draw your attention to the importance of causal mediation analysis. Because I know that past analysis has been widely used for such a long time, but I want you to think very hard about their limitations and the importance of conducting sensitivity analysis. And in our slides at the very end, we see another section on how to write a causal moderated mediation analysis paper. I would not cover that now, but I would like to read them after today's workshop, because I hope this can provide a template for your future paper writing. And at the very end, I have some references for your future reading. And these are the papers that I published recently. So these are other references on other topics. If you have any questions, feel free to email me. I'm very happy to see all of you. Thank you for staying late. And I hope you all have a great day or a good night. Okay, thank you.
你好。
Yeah, any questions? Yeah, I would also like to thank Jane for the Oh, by the way, I will share the updated slides.
Any questions?
Yeah.
If not, we'll conclude this workshop. And thank you, Professor Qin, for your wonderful talk. And we all learned a lot from this workshop. And we will send you the recordings or the link to through email after this workshop. And please reach out if you have any other questions or would like to discuss. Okay, so that will be the end of the workshop, and
Yeah, thank you very much. I will share with you
Yeah,
the
have a good
updated
day.
slides and our solution. Okay, have a good day. Bye.
Okay, bye everyone.